Hello, everybody. My name is Chris Lubkeman. I'm the head of the Strategic Foresight Hub here at the ETH in Zurich, and it is my great pleasure to be the host of a dialogue today. And this dialogue is part of the AI Center's series. It's a collaboration between the AI Center and the Strategic Foresight Hub. And the AI Center has been sponsoring these sort of a trilogy of activities with selected faculty. And the trilogy is a spotlight, a lab, and a dialogue. In the spotlight, you can see from our guest on YouTube or on the AI Center website. Then there's the lab, which we will be hosting soon. I don't believe we've had that one yet, unless I missed it. And then we didn't have that yet, did we? No, good. Phew. And then the lab is where we actually dig in deeper to some of the topics. And then, of course, there's the dialogue, which we're having today. Now, this is the fifth and the last in the cycle for this year. It's been a great, great series. And the next event for the AI Center will be the AI plus X Summit, which will be on October 15th. And I encourage all of you to think about participating on that day. It's going to be actually a pretty cool thing. So excuse me. So today, our topic is AI and artificial reality, or AR. And there's no one better to have this dialogue with than Professor Otmar Hilliges, Associate Professor of Computer Science here at the ETH. So welcome, Otmar.
Hello, thank you for the introduction, and welcome everybody. Looking forward to this chat.
It's great to have you here. So, Otmar, you lead a lab, if I'm not mistaken, it's called the Advanced Interactive Technologies Lab. Can you tell us a little bit about that?
About the name or about the lab?
Well, a little bit of both. Go a little bit of both, yeah.
Every lab needs a name, right? So exactly. It has a name. So the AIT lab here is a collection of great individuals. We're interested in kind of the foundations of the perceptual elements of almost any AI system. We are particularly interested in applications in robotics, augmented reality, and virtual reality. Hence, I guess I'm here today. But it's really, the questions that we're trying to answer is how can an artificial agent of any kind navigate and understand a human-made world, right? And that requires understanding where people are, what people are doing right now, what they may do in the future, right? We can kind of hypothesize about, our peers' next actions and plan accordingly. And this is something that any significantly advanced AI system will have to do or will have to be able to do in the future. And that's really the questions that motivate us.
So you're looking at both the physical environment and as I understand it from you a little bit more importantly is the humans within that environment.
Yeah. Traditionally, I think, those were understanding the geometry of the environment, the physical environment, and then let's call it the traditional academic titles would have been, activity recognition, action recognitions. Those used to be like almost separate strands of research. And in that traditional view, I'd fall into the human-centric side of computer vision and machine perception. These days, it kind of grows back together because you can't really reason about what humans are doing if you don't understand what their environment is.
Sure.
But still, the speciality is more on understanding humans, modeling human activity, rather than, let's say, creating a very accurate 3D reconstruction of the world around us. That would be other people here at ETH.
So it's very often said that, of course, when you're talking to two people, that the facial signals which you're receiving are by magnitudes greater than the verbal signals. So is this what you're working on, trying to understand those?
It's not the only thing, but it's certainly an important aspect. Yeah, and that's actually one of the underlying motivations, at least for myself. Because not only facial expressions, body language, everything right? I said something you thought that was interesting and you leaned in,
Yeah,
right?
yeah,
And
exactly.
that
Yeah,
tells me what you like, what you
yeah,
don't like.
yeah.
And you know, how we say things, how we carry ourselves is like a very important communication channel between humans, and it's a communication channel that machines cannot interpret at the moment at all. And so we're not really there yet, but we are building, you know, algorithms in terms of understanding really the fine-grained motion of people with this application scenario in mind, right? That we get a better channel to communicate with, let's say, an artificial system in a similar rich way that you and I can communicate.
Mm-hmm.
That involves not only speech. Again, that's a special area. Computer science is highly specialized these days, of course.
Sure.
But yeah, really having algorithms that could interpret body language, facial expressions, these kind of things in a much richer way, is certainly one of the sub goals of our research.
Mm-hmm. So what got you started in all of this? Take me back to Chicago. You know, where
to
you go?
Chicago. I have to take you back to Munich
Okay.
in that sense.
But Take Me Back to Chicago is a song, you know. That's
Yeah,
you know.
yeah, yes.
Okay.
It really was early contact with what is now known as augmented reality. So during my studies at Technical University in Munich, I was involved in, you know, student projects in a research group there that specialized on medical augmented reality. So they really wanted to develop technologies that help surgeons, you know, plan surgery procedures and so forth.
Yeah.
And back then, you know, augmented reality was terrible. It really was. I mean, we had a little bit of a chat earlier on, you know, the simulator sickness, but tracking was terrible. You had to instrument everyone like for, you know, 25 minutes, and then they saw a 1 minute long demo, and then it was 25 minutes to take all the crap off the body again.
Yep.
And so I was both fascinated by the technical challenges. How can you overcome a lot of these limitations? How can you make that 1 minute long experience real? And you know, there's a second component. Maybe we need to talk about both. That really also hooked me into that application domain, and that was really, you know, that 1 minute long experience, that 1 minute demo where you have computer graphics appear spatially registered in the world, where you kind of are able to walk around, where you actually back in your body and you're interacting with digital information. And that seemed to me like a fundamentally better way than sitting in an office chair all day long. So I'm motivated by both, right? Like by the technical challenges and making augmented reality a reality is still today a very difficult challenge. And there's lots of cool research topics in that whole
domain.
universe. But I also think like the computing paradigm is a very promising one.
I think so. If we take a look at the past, so for me, if I look back 25 years, when I first was looking at this, or if I first was confronted with it at MIT, and what we were talking about, where you've got these massive goggles on your head, which you barely hold, you're on your neck, could hold them up, and then after 5 minutes or 3 minutes or even 2 minutes, you'd want to go vomit, right? Because it was so in motion sickness. And we think the leaps and bounds we've come to today in those 20 years, if we take that another 20 years forward, if we think of where you're heading with this, with miniaturization, with the algorithms, what do you imagine that, so 10 or 20 years, what do you imagine it's going to look like?
I could imagine that that's probably a time frame that's long enough for something like you know, today's augmented reality to really fit into glasses like these, to be as lightweight as, you know, just an additional piece of garment that you put on, and to actually have become usable by then. So those are, I think, there's many challenges, but of course the form factor and what I casually call the walk up and use dimension of this whole thing is something that's not quite there yet. Right?
Tell me about that, because you say actually be usable.
Yeah.
That's an interesting 3 words to put together with this. Yeah. What do you mean?
Yeah. I mean, there's where do I start here, right? There's computers,
Well,
and laptops, and they're extremely powerful machines. But there's a very different paradigm, even your smartphone and tablet, right? That you can throw them into the same category as far as I am concerned. They require you to kind of instruct the machine to do something, right? You type a command or you click on a button or whatnot. And then, the machine just sits there and waits and does something. And I think once we really bring information into our 3D environment, into the physical world, and we have, displays plus sensors on our body that perceive what we perceive, plus the power of AI behind it, you'll have a system that can proactively interact, right? Think of it almost like there's this German, I don't even know if it's German, the children's story with Abraxas, the raven that sits on the witch's shoulder, right? That's kind of what I have in mind, that you have a digital system that kind of perceives the world around you, can occasionally go off and do stuff by itself and bring the information that you require or that we require when we need it, right? That's it's not my vision.
Sure.
That vision has been around for a long time, but I think it really is a different computing paradigm from how we use our devices and computers today.
We had a brainstorming session this afternoon talking about the idea of the human digital twin. And out of that, something came up we called the digital angel, which was if you have a human digital twin, you can test out therapies on your digital twin before they're given to you to actually determine if it's going to be good or bad. Or the angel could tell you, hey, that an extra half hour of sleep could make a huge difference in your life or not. This is sort of like the raven, which you're saying that this part of your vision is in a way to help. But that's what I'm trying to think about, the machine perception, how that fits into that. So your glasses are going to be saying, hey, watch out, that person's going to come attack you, or that car is about to hit you.
Yeah, yes, to some degree, I'm talking about context sensitivity. I guess this is what you're referring to here.
Yeah.
But I also am referring to adaptation, right, to that context in a nonstop fashion, right, by knowing what I am doing, where I am, whom I'm interacting with, right? Like think about like simple things like the constant notifications that you get on your smartphone these days. Right? If your display is basically glued to your eyes, we want to be a little bit smarter with when and for what reasons I interrupt you. Right? If I have the 3D world as my display, right? It's an infinite canvas potentially, but there's certainly some areas that I do want to use to show information and others that I don't. If I'm talking to you, right, I don't want like any kind of information blocking your face and whatnot, but maybe I do want like some information. Hey, you met this person a long time ago. And so for that, the system really must understand not only where you are in the sense of here's my GPS location, but it also really must understand what am I looking at? Who am I talking to? What is that person doing? And potentially, if you want to really adapt, information display in that kind of context, you also really need to have some way to predict plausible futures, right?
Yeah.
You need to be able to say like that person is going to get up and walk out, right?
So it's sort of an anticipatory, like the anticipatory algorithm saying, yeah, odds are they've been sitting there for an hour and a half, they're going to be getting up soon. I mean, that's what. But how do you teach an algorithm? I mean, are you focused on how the algorithm's learning this or teaching? And how do you do that? I mean, is it you just kind of sit there, okay, A, B, C, D, E, F, okay. How do you do it?
I don't think you're going to get to a system that scales to the complexity of the real world if you were to do that, right? A lot of the technical work that we do, you can classify it as kind of deep learning based human-centric computer vision. So there's a lot of algorithms that come out of machine learning in particular, neural networks and architectures and whatnot. And I would say, in the last decade, a lot of that work was basically, I'll show you lots of examples, and then these algorithms learn to almost memorize the data that you've shown them. What we know now is that they're very, very sensitive to the training data, right? As soon as something shifts a little bit, distributional shifts, the performance suffers. Let's say it like that, right? And so there's limits to there's still some people that believe you just need the right data and you will be able to learn everything, but there's limits to this, right? And so to us, it's also really interesting how we as humans can, generalize across so many different tasks, how we do not suffer from this sensitivity to distributional shifts, and how we can bring some of this ability to the types of problems that we're looking at. And one concept that's super important there for us is the idea of, prior knowledge and inductive biases, right? Like if we know that we're looking at people, then we also know quite a bit of, prior knowledge about what humans look like, what they do, and so forth. And building these into the algorithms such that they can learn better from fewer data samples is really what we're specializing in the lab here.
That's interesting. So tell me more about how do you actually acquire or make this prior knowledge data? I mean, how do you do that?
There's a very simple example. This is already, something that we have done in several versions. I don't want to say we're rehashing the same recipe, but we're kind of learning more about it.
Sure.
But this goes back to a piece of work that I've done with one of my earliest PhD students, let's say 4 or 5 years ago, where you basically take not even the inside, but that you're looking at humans, right? That there's a skeletal structure, we know shoulder, spine, and whatnot, very simplified representation of the skeletal structure. And we know that this somehow has to move in a coherent way over time, right? So you can build a graph over space and time, and then design an inference algorithm that reasons about, okay, the head was here in this frame, so it can't be very far in the next frame, right? And this has been done in computer vision for ages, but building that into the learning algorithm and designing both the training algorithm and the neural network architecture in a way where it benefits from this knowledge is what makes it technically challenging and also leads to increased performance. Right? Because the network doesn't have to discover the structure in the data. It's already there.
Is that, and so I know within this world, there is a difference between supervised and unsupervised learning. Are you describing a supervised learning mode? Is that what or is this unsupervised or?
This actually falls somewhere in between, right? So you train it in a supervised setting, but where you require less data, or with the same amount of data, you get better performance because you don't have to discover structure in the data, right? You already have the knowledge. You only have to parameterize the structure. So, but that's a very good keyword, right? I think like the future goes more and more towards what's now called self-supervised learning or unsupervised algorithms.
And what does, when you say the future, what are the implications for you as a researcher? And how you...
that we never run out of problems.
Woohoo! That's great. Fair. Okay.
No, the other implication, of course, is that it never does get boring, which kind of, if I'm very honest, is one of the root causes for me doing this job, is that I constantly learn and discover new things, right?
Yeah.
But the consequence is that maybe for a while in computer vision, it became like a game of the data matters more than the algorithm. And if you go back to, or if you not go back. If you go forward, let's say, to more self-supervised, unsupervised techniques, I think the algorithm becomes to matter, or starts to matter more again, over like, do I have all this annotated data that I can get? And I find that intellectually more stimulating and interesting.
Because you mentioned this in your spotlight, which everyone should go and watch, that there's this sort of difference, the two schools of thought. One's a data-driven and the other is iterative. This is, I think, what you're referencing right here. One is, or is that not, just a massive data sets, and the other is like, let's just keep trying and trying and trying and trying.
Yeah, I think what I'm talking about in the spotlight is connected to our current discussion, but it's not a direct reference to what.
Okay.
Yeah. Yeah.
Okay.
But yes, yeah, I think that, I mean, there is definitely a purely data-driven perspective to this, and then there is this perspective of, hang on, if we know a few things, like why do we waste data, and why do we waste compute cycles on that, right? On discovering what we already know.
Yeah.
I tend to not want to be that wasteful.
Yeah, fair. Well, that's fair. I mean, this is just it's a good thing not to be wasteful. And these days, because we don't have those resources to waste anymore. So that's
exactly. Yeah.
Yeah. So what is for you the biggest challenge in your work? Is it data? Is it people? Is it time? Is it computing power? Is it algorithms, mathematicians? What are some of the biggest challenges you face in your work?
All of it. It's not a valid answer, is it? Right?
Nope,
But it is.
Sorry.
It is a combination of all of the above. In particular, because we're looking at human activity, we're looking at humans getting data that is useful and that allows us to do new things is certainly a very, very interesting challenge. Designing algorithms that require less of that data is part of your answer to part of our answer to that challenge.
Sure.
But there's also one thing, we've kind of talked about data in general. There's also the challenge of observability, right? And
interesting.
So if you're talking about humans, then yes, you can look at pictures and you can look at videos and you kind of understand where we are and what we're doing at some level. But if you're thinking about the raven that sits on my shoulder and wants to be useful, the virtual raven, then it kind of needs to reason a little bit about intent, right? It kind of needs to reason about things that you cannot observe directly, right? Like what you want, what your goals are, and so forth. And kind of, this is the long-term goal and long-term challenge, is to get to some of these unobservable states that an observer, either myself as a user of an augmented reality system or the people that I'm interacting with, right? What is their internal unobservable state? We can't do this to a high degree of accuracy, but we can reason about it and we can guess, right, what your intentions are.
Yeah, so infer through various signals.
Yeah, and so we have dabbled in that area. It's not really my expertise, but this is really like the long-term goal is to figure out, what does someone want, at least over a short time horizon, right? Like in the context of the current situation. I don't think it's going to be feasible to reason about your long-term, your life goals from, let's say, a snippet of video or whatnot, but your short-term intentions may be possible to infer.
So that means then, if you're at a negotiating table, if you and I went in together to negotiate a contract with a new supplier, and we both had augmented reality, AI-based glass, say the HoloLens version 10, your work is going to help tell me exactly when that person across the table from me is bluffing and when I can push and when they can. Is that am I fantasizing, or is that actually something which we could imagine we could get to?
I mean, this is not a scenario that I personally had thought about, but
Mm-hmm.
I mean, for sure, there is people in the larger community that are working on, understanding, recognizing emotions, predicting emotions, and so I think, if you take that work that's typically looking at facial expressions together with body language, taking together with, maybe some ontology that goes on in the background and brings you all the data that you need to know about your negotiation partner.
Mm-hmm.
I think that's something that could be feasible if it's desirable.
Mm-hmm.
Different question.
Well, it could be maybe I want it before the other person across the chair does. So it would not be desirable that my opponent would have that on my,
It becomes a question of who has the better technology.
Exactly, and who gets there first, right? And that's but this guy. So
I mean, we like you bring up negotiation, right? I'm actually thinking of systems that can help us negotiate maybe daily life, maybe we're thinking about people that may have challenges in doing that.
Give me, for example.
You could think of someone who wants to stay independent, who may be aging a little bit, right, and who wants a little helper that can kind of predict something. And there, like, these short-term predictions become super important, right? Like, think of this very, very simple scenario of maybe you're I don't know, like 25 years older from now on, and you struggle getting into your jacket, let's say,
Sure.
or getting dressed. And so if I want a robotic system to be able to help me in that setting, it really needs to understand, what is my spatial configuration? What is it going to be? What are my limits? And it needs to be able to do that in a planning setting, right? Where I then can position the garment correctly so you can put your arms in and whatnot. So that's maybe a more positive spin on kind of making short-term predictions.
That's actually, that's really quite fascinating. I hadn't thought about that. So you're saying your perception, because I just had a shoulder surgery and it's still very difficult for me to put a jacket on. So I'll call it the home butler could help in a way that could be something which could help me live better at home.
Yeah, and that would be certainly for today's perceptual algorithms that would really be pushing the limits, right? You could find individual papers that maybe reconstruct the detailed geometry of your shirt. You could find another paper that does a pretty good job at telling you what is the exact spatial configuration of the underlying skeletal structure. But you couldn't put these together and have the robotic little helper today. That would not be, that really would be pushing what's possible.
Interesting. So you also focus with your work on of the room perceiving what the person is doing. This, if like with Alzheimer's, just dementia, when you could begin to see things, signs, which anyway.
Yeah,
my point.
Yes. So I mean, the question of interaction, right, is something that drives me and that I've looked at from many different perspectives. And in the last, what has it been, probably 2 years or so, this question of, can a system, an artificial system, reason about not only the human body and the parts of the human body, but also the way we use them to interact with the world, right? Like picking up objects, maybe opening and closing things, and really dexterously manipulating objects, has become a very hot topic in research right now. And I think it's really an important step in a future towards a future that I've just described, right? So really the key is in the interaction, right? Like, why am I doing the things that I'm doing? I'm doing them because I want to change the state of the world, right?
Yeah, no, actually, that's pretty cool, especially when you're thinking about, as you said, individuals who might need more help, right? And then you're able to perceive what they need, and then provide that in a way, which is quite intriguing. So let's come back. I want to come back to because I think you in your professional career also have worked on the HoloLens, right? Is that correct?
At the very
Or
beginnings, yeah. Yeah. So some of the work that I did during my postdoc was then used to basically launch the incubation effort within Microsoft.
mm-hmm.
And then, the ETH knocked at my door, and I kind of decided to pursue that opportunity, and other people took over the commercial side within Microsoft. But I'm very fond of that project and very excited to see how far it's come.
Yeah, it's coming. It is pretty cool as it's coming. Let me ask you this. For me, what's quite curious is the difference between, I'll just call it onboard computation and cloud computation. Mm-hmm. Especially when you're looking at your work with this perception, this perceptibility. Mm-hmm. Now, where do you see that heading? Like with the clock speed of the chips and et cetera, what's needed in order for you to be able to execute what you're hoping to be able to do?
I would say we really push the boundaries what even modern compute systems can do. In our daily practice, it's actually more on the compute cycles that you need to learn the parameters of these algorithms. So we're running this on big GPU servers and everything, but also inference time. And I think that's what your question is actually getting at, is super important in this setting for several reasons. One of them is we can actually move pretty fast. I mean, now you and I, we're sitting here and chatting for most of our days, but if you just look at your fingers, right, like you can move them pretty damn fast, and so you have to process this quickly if you want to be able to respond to all types of human motion, right? You have that picture behind you of people playing with a ball. That's always a good example of very fast motion. And if you're talking about, let's say, either the augmented reality system that can display some useful information around, I don't know, you watching someone playing sports, or you have that robot that's supposed to get out of your way as you're running down the hallway, right? Then you need to be able to process this information really in real time and be able to close the loop in a millisecond computational budget. And that pushes modern architectures, right? More modern compute architectures. It's not something that we work on in particular, but it's clear that that challenge is there. And in particular, if you're talking about visual information that's directly embedded in your visual field, it becomes super important. You're in your own anecdote, right? You said 25 years ago you wanted to throw up after wearing the early VR systems. In augmented reality, you have the challenge that you really have to compete with the photons of the physical world, right? Like everything else is rock steady. You move your head, nothing. There's no latency in any of that. And now if you're rendering virtual information that's registered with this world, but doesn't have that same property, right? You move your head and it kind of swims a little bit over here. You'll notice this instantaneously, right? So there's very, very little room for error.
And is that a good thing or a bad thing that you notice it?
Again, it depends. In VR, it's a bad thing, right? It's known that is, one of the causes for simulator sickness, and different people have different levels of sensitivity there. In augmented reality, seeing the real world does anchor you, right? And so you have less of a conflict between your visual system and the inertial measurement unit in your inner ear. So simulator sickness is less of an issue. But if you're thinking of global population scale systems and something that could really replace your laptop or maybe even desktop computer, then even that small fraction of people that find it disturbing would be a limit, right, to rolling this out. So
I'm just sitting there thinking, you get rid of the laptop, where's the computer? How is that going to work? I mean, seriously, this kind of, if you imagine that, because it's like, how will that start to interface? Could you also work on interfaces or no?
I have done that in the past. Currently, not so much. With more on, what I have talked about earlier, the context adaptation, figuring out what your internal states might be, and then displaying the right information, that we have certainly looked at and look at further. What really are the means of interacting with the virtual world? To some degree, the answer lies in, well, we're thinking at least part of that is going to happen in ways that are similar to how we interact with the physical world. And therefore, a lot of the focus on understanding how we interact. But yeah, the interface itself, I think, is something that actually, the commercial entities in this space have to figure that out to some degree. And it's maybe... There's a rich history of academic research on it, but I'm not sure if those are the most pressing academic questions at the moment.
Yeah, so just a quick pause. This is the commercial break for those who are listening in passively to become active and pop some questions into the chat so that you just don't have to listen to me asking all these questions. You could ask some of your own. So I'd encourage you to do that and pop them in there and then I'll weave them into our conversation. So there's the commercial breaks over. So if I want to stay with the interfacing, because perception has a lot to do with interface, right? And this is, and for me, how I interface with information, how the machine interfaces with information. Our visual cortices are pretty flippin' amazing. How they filter, put the information into up here, and then all the different layers that we go through to be able to decide what's important and what's not. Right. And I guess and that is so much of what you're trying to do is helping the machine to understand what is important and how to interact with the human. So one of the questions is how hard is it to understand human action?
It's on a scale from 0 to 10. It really depends on the granularity, right? And it depends on it. Yeah, it depends on what you want the answer to be, right? If I'm given a small set of potential actions that I know that are going to appear, and then I just have to classify, right? Like this action appeared at this moment and this action appeared at that moment. That is a doable task, right? If I'm giving, like just any random sensor input from the real world and I'm supposed to make sense out of it, that's, we're then talking about the difficulty where we will require a couple of decades to solve them, right? So general understanding of human activity is way off. And it may be impossible due to the unobservable nature, right, of what's going on inside of your head.
Exactly.
And so, yeah, sorry for dodging that question. But it depends. No. The answer clearly is it depends.
Well, Otmar, I'm very sympathetic to the answer because people always, that's exactly the answer I give to almost anything. My kids always used to ask me, or my students when I was teaching, it was like, well, it depends,
Yeah.
What do you really want? Like, this is in German, as you know, wozu is to me, one of the most fascinating words in the German language, which doesn't translate to English at all. Is wozu, like what's the goal? And so I think that's really cool. So if we're taking a look at your, like this perception, I'm going to pull a parallel to cars for just a minute. And, cars have a very difficult time discerning when there's hail and rain and sleet are all happening at the same time. Their perceptual system, which is an algorithm, which is on board, that is a dynamic loop, a dynamic system layered on top of a static one, right? So is your work also applicable with that, or is that work applicable to you, or is this just it's an irrelevant question? I'm just curious. Where is that?
Again, I think it depends on your, where you are on the ladder, climbing the ladder of abstraction here, right? I think at the highest level, they are the same problem. right? Like if you want to be able to, let's say your glasses have a camera that's facing out into the world, and you want that system to always work, no matter what the weather is, no matter what time of day it is, whether you're, in a subway, in a dark tunnel, on a beach in Jamaica. Those are very, very different sceneries. And if you want that system to work always, then you have the same problem that a self-driving car faces. I would even say that something that you wear probably is even harder than the problem that self-driving car faces, because there's indoors, there's outdoors, there's small enclosed spaces, there is the the outside with all its variability, and you're not really bound to infrastructure, where most cars most of the time stick to streets, right? And most of the driving happens on at higher speeds, where you basically need to know where the lane is and where the other cars are. Inner cities are a different topic. So that's probably the closest overlap, right? If you have a self-driving car that needs to navigate mixed traffic situations, where you have cyclists, where you have pedestrians, where you have kids emerging between parked cars, and you need to react to those. That's certainly where the same type of algorithms that we're looking at comes into play. So that's where the intersection is. But then I would say, those things that happen inside, that happen, in a situation where you have a group of people. I know we're not allowed to do that right now, but
no.
Oh, really? Those settings, you would be harder to encounter if you're a self-driving car. So there's differences, but there's certainly an overlap. And the community, the larger computer vision community that we publish our papers in, certainly touches upon both of these application domains.
Yeah. So if like every once in a while, I've seen what the computer model the environment of and a car, and it has all these abstract things. When you're modeling a human, if I would be looking at the graphical representation or the representation of your model, what would that look like?
A couple of years ago, it would just be a stick figure.
Yep.
We're now getting to a level of granularity where we really start talking about at least the whole body, including there's the shorter, thinner people, there's taller, heavier people, and whatnot. And people start looking at really understanding clothing and the geometric details. This is certainly like a current research trend, that you're really trying to model the small details. And that's partially driven by academics need to do something new. If we understand how to model that stick skeleton, then you need to find a new problem. But also, if you want to escape the question of where does the data come from, then eventually you want to have a representation that's almost indistinguishable from the real one. So I can simply take it, generate an image, and fit it to an observation, right? If I can't do that, if I can fully explain the appearance of my observation, then I must develop some underlying understanding of that scene. And that's, I think, where things are going, right? That we have generative models that can be controlled. Let's say I can generate faces, and I can control how long the hair is, facial expressions, all these kind of things. And if I have these knobs, then I can fit my generated images to the real world, right? And by having done that successfully, I know what the parameters of the real world are, the underlying parameters of the real world, which is what I may be interested, right?
But isn't this what Hollywood does already?
Yeah, so that, there's a strong confluence now of computer graphics and computer vision techniques. What Hollywood does clearly is driven by a human artist, right? That knows what they need to do, and they really only care about the appearance in the end. What we care about is like an algorithm that understands what are the things that I need to change in order to match the appearance, right? I'm not interested necessarily in making pretty pictures. I'm interested in understanding the underlying parameters.
Okay.
Right.
So if we take that, just go with my abstraction for just a moment and say, if you're successful, then we don't need actors anymore. Because you'll be able to program, because it'll be perception. The machine, if you will, the algorithm understand what's going on, and you'll be able to tell the algorithm this is what I want, and they'll be able to kind of pop it back and forth.
Yeah, so I must do a terrible job in explaining this. So my PhD advisor always gets angry at me when I say that, because he says like you can never automate creativity. But that's not what I want to do.
No, I didn't.
That's not what I want to do. But I'm saying this, right, to avoid this misunderstanding. We're not trying to take artists' jobs away, right? We're trying to get to a state where you really, so the image that everybody sees of you on the screen, right, is because of a lot of underlying parameters, some of them being static, right? Your identity and your genes and whatnot. Some of them are due to your current state of mind, your emotions and whatnot. And yeah, exactly, right? And an artist has like an intuition, right? Like how do I need to, render a face or, to evoke these kind of things. And we have an intuitive way to interpret them. But I don't think an algorithm will ever develop anything like an intuition, right? So a robot or an augmented reality system, to be able to reason about the world at the level that we do, kind of needs to extract information and not an intuitive understanding, right? It needs to at least have a probability of what your emotional states are. It has to have, some numbers, right? And that's what we're trying to get at, so that I can there's a lot of research in being able to generate with control over as many of these knobs as possible, so that I can fit that generation to an observation, and then I know what the underlying parameters are. Right. So that's different from wanting to create a movie. It may be possible to use the same techniques in the same algorithms in the creative industry as well. That's not necessarily the research that my group is doing.
So, and this is the last one on this, and I want to move on to something. But so, as part of the perception work you're trying to develop is also being able to understand, like, I'm coming back to this as perhaps like facial expression. So like you can tell when someone's about to laugh or someone's about to cry, because that then also has an impact perhaps on how their body is going to move. Is this so?
Yeah. So this is certainly something that you would want to be able to do, right? For example, if I want to change, let's say I have lots of pictures of you, right? And I want to in the setting that I just described, I generate so I can understand. If I want to form a hypothesis, like, oh, maybe, happier fits better.
Yeah.
Right? If I want to change the resulting facial expressions, I must make sure that the static properties, right, your identity doesn't change.
Yeah.
Right? And that's where the research challenge lies, in being able to disentangle all these properties and states, and to gain control over it, so you can understand.
So do you also have like anthropologists and psychologists in your team?
Not in my team, no.
Okay.
No. We're probably also not at the level of fidelity and analysis that these guys are interested in. There's certainly, there's intersections with, the neurosciences, cognitive sciences. Anthropology, I know close to zero about, and there's not that many of those here at ETH.
Yeah.
But yeah, I mean, to some degree, a lot of the algorithms are at least inspired, right, by what neuroscience believes it is how we humans do things.
Yeah.
It's nowhere near, a blueprint or anything, but of course, our capabilities are often like a motivating element. It's like, hey, we can do this. Let's try to see if a machine can get at least close to it.
That's really cool. That's really cool. So when you so this, I have two, maybe three questions before we have to end. Number one, how did COVID impact your research? Did it give it more impetus? Did you make more clarity? Just was super frustrating? Just it's purely it's actually just a personal interest. I'm just kind of curious the impacts of COVID.
Yeah, when it hit, I thought it would be really, really bad for our research. But to some degree, I guess as a computer scientist, we're the luckiest of a bunch in that setting, because a lot of the technologies that we develop and that we're also proficient in making use of, right, helped a lot. Clearly, the experimental side of things, like actually maybe recording data or trying things with pointing cameras at humans, was difficult for a while. But it also brought new inspirations. We started focusing more on telepresence type of problems, or problems induced by telepresence. We actually we started a project that kind of specifically looks at analyzing human behavior in a video conferencing setting.
Oh, really? Interesting.
So, it's one project out of many, but these were kind of the realities around you definitely influence what is going on. And I think telepresence itself goes beyond COVID. I think some of the behaviors that we as a society display are definitely not sustainable. And so augmented reality, telepresence, these kind of things can at least help.
Absolutely. So. And there's some things I would argue are even easier with online. So the transactional is why you fly halfway around the world to do something that's transactional, stupid.
Yeah. Certainly a lot of things that probably 2 years ago I would have said, like, no, you must do them in one-on-one, and technology is just not there. We have all learned that they are possible already with the technologies, but clearly they would be easier, and we probably would continue to do that, or we may continue to do some of it virtually if technology was better, right? Like right now we're doing a lot of it because we have to, because of circumstances, and getting systems that say like, hey, it's actually better to do this virtually than to take a train or hop on a plane is something that we need to get to.
That's so. And so when you were fished to come to the ETH, right? What was it about the ETH that attracted you?
I guess excellence is probably the main motivation, right? It's excellence in geography.
Well, hey, location. Those are two. Yeah. And are you hiring in your team? So if someone watches this from after, so are you looking for new?
Absolutely. Yeah. We're always looking for talent. We have a great team, but the unfortunate nature of PhD students is that they graduate at some point.
Darn it.
Once they know how it works, they go and do it.
You can fail them, and they just keep them around for you.
No,
I'm just kidding.
They're fantastic folks, and they're gonna have impact wherever they go. So, but that means we're always looking for talent, right? So
absolutely, always, yeah. So if you look out to 2040, that's 20 years from now, plus or minus, what's your vision for 2040? Describe that world.
Describe that world. Yeah, that's interesting, right? Was it Bill Gates about, predictions are hard, especially if they're about the future?
Yeah, they're very difficult.
I think that, that's such a long horizon that I almost don't dare making an informed decision.
Come on.
I can dare dream, right? Like
that's what I want. Yeah, dream for a minute. Give me 2 minutes of dreaming.
If society still hasn't gone off rail entirely, then I'm pretty sure that information will be present in our physical world, right? Like you won't even be able to tell what is what is real and what is not. And I'm not necessarily saying that's a good thing. There will certainly be nefarious uses, but there will certainly also be good uses, right? I think I gave some examples of
yes, you did, yeah.
How I believe the technology can have a positive impact, and I'm working on shaping a future where technology that we develop has a positive impact. That's the best way to influence it, right? So yeah, I mean, hopefully I don't have to sit all day in front of a screen in 2040. That's for sure. Hopefully, to be able to talk to you, I don't have to, I don't know where you are right now, but I don't have to actually physically move. I may be able to just pop over, to family in the States, to family over in Germany, and really experience that as if it were real, right? And I also think that a lot of the technologies that we are developing right now, and that hopefully we will be pushing over the next decades, will also help some of the people that may not have all that many, friends and family, and may, sit at home, may have disabilities, and maybe have like a little Raven Abraxas that keeps them entertained.
Oh, you know what, Otmar? I just discovered people have been putting the questions into the Q&A, and I haven't even been looking through them.
You advertised
it. I did. I just got so into it. But I'm going to ask you, there's a couple in here. We've just got a few minutes left. How does self-supervised learning relate to reinforced learning?
Reinforcement learning, yeah.
Yeah.
So maybe I'll answer the second half of the question. Will it play a crucial role in the future? Yeah, I mean, reinforcement learning clearly is a very fascinating area of machine learning. I'm not really an expert in reinforcement learning itself, but the intersection of some of the perceptual problems that we're asking and then putting that into action clearly falls into the domain of reinforcement learning, right? So, and some of the things that I've described in this Q&A are actually are in the mathematical framework of reinforcement learning. So if you want to adapt, for example, an augmented reality display that is really context sensitive, that is a decision problem, right? And a decision problem is best modeled as currently by the reinforcement learning framework. So all the times I mentioned an agent making decisions about what to display when, to reason about, the state of the unobservable states of humans, those are all references to reinforcement learning.
Okay.
For those that know what that means.
Okay, that's good. Well, I don't, and I appreciate that explanation. I apologize to you, and because I just was so engrossed in our conversation, I kind of failed at my hosting. But do you believe in the convergence that humans and AI are going to be becoming one? The question is slightly different, I mean, the singularity. What's your view on the singularity, Otmar, in the last 10 seconds? Do you believe in the singularity? Yes or no?
The singularity? No. I don't.
All right, good.
I don't. I think I mean, that's not saying we're super special, but I think like technology and technological systems are fundamentally very different, and that doesn't mean better or worse, right?
No.
They evolve in their own way, and they may supersede us in almost all the capabilities, but I don't necessarily think that at some point we're going to disappear into technology, if that is what the singularity requires.
Yeah, well, there we go. Well, thank you, Otmar. Thank you very, very, very much. Again, I apologize to you for not getting those questions because I was just so into our conversation, which is, for me, a great sign of what your work, and it's so fascinating, and a terrible job as a host today. So I apologize, Dad. I want to thank the AI Center as well, Daniel Barnbeck, and everyone else who was involved in helping make this happen. And I want to wish you really all the best of success with your research, with your work. And I look forward to seeing it. And stay safe, stay healthy. Thanks everyone for joining us. And I'll see you in just a little bit.
Likewise, thank you for your time. Thank you for a great question round, and I'll see you around.
Okay. Ciao, everybody. See you soon.